Okay, hello. Sorry that this video kind of came in a little bit later in the break. It's just because my voice is now finally feeling more strong and better than it once was before. It's still kind of sick, but it's not so bad. Okay, so the purpose of this video is for us to kind of clarify some definitions about simplifying, factoring, and solving. And the reason why I want to highlight these is because I still see some of us still doing more work than needed. Okay, so that's why I wrote this here: work smarter, not harder, by at least reading and looking at your context clues about, okay, what is this problem asking me? How do I solve? Or like, what does it mean by solving? Does this mean to find the zeros? Does this mean to pick the best zero to represent a world situation that's more realistic, or am I just factoring and I just need to break down this polynomial expression, right? And so I'm just going to give us a couple of definitions here, and so that way we can move forward with this piece. Okay, so to simplify, I know these arrows are kind of like messed up here. So to simplify, all this really means is to rewrite. So we want to rewrite by writing in a compact manner. Okay, so usually when you're doing this, you are combining like terms, uh, using distributive property, and all the other properties, and so on. Okay, that's kind of like your idea of thinking that way. Now, this is not like the formal definition, but somehow how I like to remember this is either like I'm expanding it or I'm building up my polynomial expression. So I'm going to put it like a little side note and say like this is building up or expanding. That's kind of like what simplifying is. Okay, to factor, this is a number or an algebraic expression by which another is exactly divisible. Another is exactly divisible. Now, for this is kind of thinking like, okay, if simplifying is to build up or expand, like this factoring is more breaking down. Okay, breaking down. And the key piece about this is it's breaking down into other factors that are exactly divisible, right? And the best way that I can show this is like, think of like 3 times 2 equals 6. Like 3 and 2 are factors of 6 because 3 can go into 6 evenly. 3 times 2, and you have a remainder 0, right? And then the same thing can be the same case for 2 going into 6. And we know that goes into 6 3 times, and we get a remainder 0, right? Now, those two are factors. And that's one thing that we've been working on this whole entire semester, or this last semester, is if we know x minus 3, we want to check if that is a factor of, let's say, x squared minus 9. Well, we would find out that it would be a factor because the factor would be like x plus 3. Okay, and we'll get a remainder 0. Now, that's what factoring is. You want to find out what are the two factors that multiply essentially to give you the product, right? It's kind of like your clues there. And then to solve is to find an exact value for an equation or expression, or for an equation, more likely just for an equation, not expression. Because usually when you're finding an exact value, you need to make sure that it's equal to something to find out what makes that true. Okay, so moving on to this piece, I'm going to just work through these examples, and I'm going to do each example, and then at the very end, I want you all to write the description for each of these in your own words. Okay, so here to simplify, again, that means to like expand or build up. So that means I'm going to have to use either distributed property, PEMDAS, or combine like terms, things like that. So we have 3x times x squared is 3x cubed. 3x plus 10 is 30x. And then I have leftover plus an x, right? And then I would have to combine like terms. I can see 30x and 1x are the same terms. So then here I can do 3x cubed plus 31x. And that's my answer. And that's it. The second one is very similar with distributed property, but there's a little bit more an extension. So we have 6 times x is 6x. 6 plus 4 is plus 24. And then we have this negative x. Now, don't forget you have to distribute that negative. So we have a negative xy. And then negative x times negative 9 is positive 9x, right? So then from there, I check to see, do I have any like terms? I do. I have 6x and 9x. And then I can combine those, and I get 15x minus xy plus 24. And that's my answer. You're probably thinking like, why did I switch these two terms? Honestly, it's just because I like keeping the constant as the last term in my expressions. It doesn't ask me specifically, but usually that's ideal if you can do that. So then factoring here, again, is breaking down into two factors that would be essentially divisible into the original, right? So then here, this is a difference of squares. So I can clearly see that with the subtraction sign here, difference of 2 squares. Now you have to remember, be a detective and think about, okay, where's the structure here? And so we can clearly see this is the structure for difference of squares, my setup. And so then here, this becomes 2x squared, and this just becomes y. And then you know from there that the terms that go into the parentheses end up being the two terms that go into your two binomials. So we have 2x plus y and then 2x minus y. Okay. I'm going to write difference right here so you all can see that. Okay. So then we have our binomial conjugates, and we can say, we could even check it out. I'm not going to do the work, but you should try it. 2x plus y times 2x minus y will give us 4x squared minus y squared. I put this one here as well, just to see like, okay, this is a difference. Maybe it could be a difference of squares, but there's just a lot of additional numbers here that it may be overwhelming. So whenever that happens, you always want to check. I'm going to put this for factoring. Always check for GCF, right? Your greatest common factor. Now here, I'm going to see if I can do a GCF, and I know I can. And my GCF is going to be 6, right? And I know that because 48 and 42, I meant 6 for just the numerical parts of the term. And I'm going to factor out a 6. And then I look at my next variable terms. Okay, I look at the one with the smallest exponent. It's 3. So then this is going to be g to the 3rd. And then I look again. I see they both have an h in common. So then h to the 4th. And this is my GCF. So then I can go ahead and kind of use reverse distributed property to figure out what would go into my parentheses here. And when you do that, you'll notice that you'll get 8 g to the 4th in this box, and then minus 7 h to the 7th power, right? And you can double check it by like distributing. 6 times 8 gives me 48. G to the 3rd times g to the 4th